elasticity has to do with ability of a body to extend its original shape and then come back to it. Ability of a body to change its shape at any point in time and come back to it. So that is that under elasticity. So there are some terminologies that are found in elasticity. What to do with stress. Stress is the force per unit length of a body. Stress has a value similar with that of our pressure, and the unit for stress is normally Newton per meter square. Then your strain is the extension divided by the original length, the value for strain. Then what other value are we the Young modulus. Then from our Hooke's law, our Hooke's law states that a body will definitely return to its original shape when you are stressing it. Steps is rather our force, or rather that one is the one I gave just now is different from what I wanted to say. So our Hooke's law says that our load, or rather the force, is directly proportional to our extension. Hooke's law. Partially, when Hooke's was trying to explain this stuff, so when Hooke's was trying to explain this stuff, he was trying to tell us that any extension, any force you add to a body, it therefore probates to an equal increase in the length of that body. That is, a body will definitely increase its extension, or rather its length, increase in length, it change in length when a force is being applied to it. So that is that on that and that. Then I told you my value for my stress is equal to the force over area. Then my strain is extension over original length. Then my Young modulo is stress over strain. So definitely this one I can make it to be equal to F over A. This one I can make it to be E over F. So I can just fix that one into this part. I'll be having F over A times, divided by E over L. So it can be equal to F over A times, take my L up, it will now be L over E. So this is the formula for calculating a Young modulo, the value for your Young modulo. I don't have enough question on this part, but I know some certain terminology on it. I have some. Take note, whenever the lateral stress is in a ratio with the longitudinal stress, it is called the Poisson's ratio, something like that. It's called the Poisson's ratio. Then I told you that a body will always remain at its elastic limit when the force you are applying to it doesn't become so great that it can distort that body. So now in your elasticity, there's a limit called the elastic limit. There's the limit where a body will definitely return to its original shape when you stretch it out. It's called the elastic limit. But when that limit is being exceeded, it is called when that limit is being exceeded, it is no longer known as the elastic limit. I think that limit is called the Higgs limit. There's a point where the body will get to it, will break. That point is called the breaking point. Hold this fact with you. Definitely, some of this stuff might definitely come out in the exam. There's something called the bulk strain. There's something called the bulk strain. Just as we have our normal strain, there's something called. Take note, this strain we are dealing yet has to do with our change in length. Take note, extension is equal to L2 minus L1. So our normal strain is the one that has to do with this value, the normal value for length. But there is a strain called the bulk strain. The bulk strain has to do with our fractional change in volume. So that is our change in volume divided by the original volume. So that is that for the bulk strain. Then I think that is that under the one I want to take you for the elasticity, because we need to cover a lot today. So then let's quickly go for the next part I wanted to explain. So the next one is linear momentum and impulse. Linear momentum and impulse. In our momentum. So the formula for calculating our momentum is normally represented in this format, P. And the formula for calculating our momentum is mass times velocity. So the value of this mass times velocity at some point in time changes. So it can be the velocity changes, the mass also changes. It can be the impulse can be between two bodies due to their changing effect. So I can throw a ball now to this wall, it hits the wall and comes back. So the relationship between the ball I threw and the wall is two relationships. So impulse can also be the relationship that exists in impulse can definitely be with two bodies. At times it can be with just one body. They can ask you to calculate the impulse for the momentum for one body, and that for two bodies also. But that time you have to determine the change in their momentum. So now the value for momentum can also be equal to mv minus u. So now the impulse in itself, impulse I is equal to the force times time. And if you can recap from what I did earlier on, you remember I said F is equal to m bracket v minus u over t. I gave you this formula. So if I cross multiply here, you'll be finding out that my ft is equal to m bracket v minus u. So my impulse, which is equal to this, is at some point in time equal to my v minus u. So there's a point where your impulse is equal to your linear momentum. It's not even a point, it's normal. Impulse is equal to linear momentum. Is equal to linear momentum. So your impulse value is equal to linear momentum. That's why they graphicalize the two under one topic. So I have some questions on this one, so let's just quickly look into it. So the first question says a resultant force of 200 Newton. A force of 200 Newton acts on a body of mass. The mass of the body is 5 kg. The time which it acts on that body is 0.5. So now they're asking us what is the impulse. Impulse is the question. How can I determine the impulse for this body? I've already given you the formula for impulse. Impulse is force times time. As simple as that. You've gotten your value, 200 times 0.5. I think that will give you 100. Take note, impulse is measured in Newton per seconds. Newton seconds. So then the other question, the one that has to do with momentum. Now they said a gymnast of mass mass 65 kg bounces vertically on a trampoline so that he approaches and leaves the trampoline with a speed. So he bounces on a trampoline. Let's assume this is the gymnast. He bounces on the trampoline and leaves the trampoline with the same speed. So its initial velocity was the same speed. The value of the speed is 9 meters per second. So now when it was coming down against the trampoline, it was moving maybe towards this direction. If it's going back, it will change direction. So our value of our final velocity must be negative 9 meters per second. Because if you are moving towards your x-axis in this way, this is the way you move towards your x-axis. If you are trying to go back, how will you go back? You will take this direction. That is the same thing with your y-axis. If you are going upward, you are going downward. If you are going upward, it's positive. If you are going downward, it's negative. If you are going towards this direction, it's positive. If you are going towards this direction, it's negative. So that's why the value of your velocity will definitely change. So now the question says we should calculate the change in momentum. Our change in momentum, which is mv minus mu, the value for it. So now let me clean this part. So my change in momentum will now be equal to, what is my mass? My first mass is 60. Okay, my mass. The mass is the same body that performed that stuff. So mass is 65 bracket 9 for the first one minus bracket mass of the body again is what? 65. This time the mass, the velocity is negative. So it will be, let's bring out the mass. Let's bring out 65 because it's common to both sides. It will be 65 bracket 9 minus bracket minus 9. So you'll be having 65 bracket 9 plus 9. 65 bracket 18. So if you use your calculator to punch that, so you'll be having 1170. 1170. Take note, momentum, like I said, is the product of our mass times velocity. Mass is measured in what? Kg. Velocity is measured in meter per second. So I can say the velocity of my impulse, my momentum is kg mass per second. So I will just introduce this. This is the value for it. So now the next one I'll be taking is expansivity. So let me just give a cap on that part. Expansivity has to do with the expansion of a body. How does a body expand? So a body definitely expands when heat is being added to it. Although force can also cause a body to expand, but the case we want to do it now is when you apply heat to that body and that body expand. So the case we'll be looking at is when you apply heat to that body and that body expand. And in that kind of expansivity, for a body to expand is when heat is being added to it, in the kind of expansivity we are dealing with now. So when you apply heat to a body, in any body at all, it can either change the shape of that body. If it's a solid, it can turn to liquid when it has to do with ice. In some places, in some cases, if you apply heat to it, that body will contract, or rather, it will bend. If it's iron, there's some iron, it will just bend. If you apply it to somebody, their state will change. If you apply it to somebody, also, the vibration will occur in the body will start shrinking, depending on the case you are applying it to. So there are several effects heat does to a body. You can apply heat to a body and the kinetic energy of that body will increase. So every single body possesses an internal kinetic energy of its own. No body is just stationary on that base. There is an intent of kinetic energy present in them. So kinetic energy expansivity is further divided into three parts. We have the expansivity that has to do with line expansivity. Line expansivity, when we are talking about linear expansivity, you can talk of wires. If you are trying to hit a wire, what will happen to it? That is called a linear expansivity. And the formula we'll be looking at that case in linear expansivity is this. Our linear expansivity is this: delta L all over L1 delta theta, where our delta L is L2 minus L1 over L1 delta theta. Then for our beta, this beta is called the superficial area expansivity, is equal to delta A all over A1 delta theta. And our gamma is equal to our change in volume all over our V1 delta theta. So these are the three values for it: the area expansivity, cubic expansivity, and line expansivity. So I said the line expansivity is when you are trying to hit a body that is just on one axis, that is the line axis. It can be a wire or anything. Then area is when you want to hit a surface like this board, surface like this. Area expansivity, it has both y and x axis, just like this board. It has its y and its x axis. Then cubic expansivity, you are trying to hit the whole shape. You are trying to hit the 3D format of that shape. You might not be conversant with the 3D format, but let me just show you. This is it. Just as we have your x axis, your y axis, rather, here's your y axis and here's your z axis. For 3D objects, if you look at your building, they are in a 3D format. They have both x, y, and z axis. So anytime you are trying to hit the whole of a body, if you carry your full cube Maggi, you want to hit everything completely. That's when it has to do with your cubic expansivity. So now let me quickly show you something. At some point in time, in some questions, they might just ask you find the value of your cubic expansivity when your linear expansivity is one value. They are giving you, but they didn't give you any formula like a v1 v2, no, or they didn't give you anyone like that. They are just giving you just your cubic expansivity. Find your linear expansivity. In that case, there's a relationship between them. There exists between the linear cubic and the superficial area expansivity. The formula is this: our alpha is equal to 2 beta, and our gamma is equal to 3. Rather, our beta is equal to 2 alpha, and our gamma is equal to 3 alpha. So this is the relationship that exists between them at several points in time. So you can interchange the values to get the value for your linear or area expansivity. So let me just give you one or two examples of this so you can get a glimpse of what I'm trying to say. Okay, I have just one question on that for today. I said an aluminium bar of length. The length of the bar is 120 meters. The temperature is 25 degrees Celsius. Its initial temperature, so it was heated to a temperature, let's use theta in this case. The final temperature was 145 degrees Celsius. So we were asked, this is our L1, we're told to find our L2, given that our alpha is equal to 9.2 times 10 raised to power minus 6. So now this was how the question looked like. So now for you to solve this kind of question, you must first of all mastermind or try to notice where this question is coming from. Is it linear, cubic, or area? Linear, cubic, or area expansivity. So if you look at it, provided it has to do with length, is linear. So you just use the formula for linear expansivity, which is our alpha is equal to L2 minus L1. That is our change in length over L1 delta theta. So now from here you can just determine your delta theta. Our change in theta is equal to theta 2 minus theta 1. So it will be 145 minus 25. If you do that, you'll be having 120 degrees Celsius as your value. If you subtract 145 from 25, you'll be having that as your value. So now, from here, let's quickly make L2 the subject of formula. I can make this one to be over 1, I cross multiply. Now, if I'm cross multiplying, I'll be having alpha L1 delta theta here is equal to L2 minus L1 as your value. So to get my L2 will be equal to L1 plus alpha L1 delta theta. So now L2 will be equal to L1. L1 is common to both sides, 1 plus alpha delta theta. So if you use this value, we're having our L2 to be equal to, what's my L1? 120. 1 plus, what's my alpha? 9.2 times 10 raised to the power minus 6 times 120. So at the end, if you solve this one, what you'll be having at the end is So if you solve this one, this is what you'll be having at the end. This is our value for it. So that is that under the area superficial and cubic expansivity. I think this is the only part your school focus on, because there are some advanced part of this stuff, but we won't be taking those ones here. So we'll just be looking at just some valid parts on it. Then I'll be introducing to you pressure, or rather hydrostatics. Hydrostatics has to do with the study of fluids. If you are talking about the movement of fluid, how fluid, what exists in fluid, but basically we'll be talking about the pressure aspect of it. So pressure now is the force per unit area that exists in a fluid. Force per unit area of the surface. The force per unit area of the surface that exists in the fluid. So our force can be equal to weight at some point in time. So I can say my F is equal to mg divided by area. Our formula for pressure can be equal to force over area, or our pressure is equal to density times height times gravity. I don't want to just write all the formula because I don't have that time now. So now Pascal principle, rather Pascal law. Pascal law says that if, for example, let me make use of an hydraulic jack. And there's a fluid present in this jack. I think it's a hydraulic press or something. That's the name of this stuff. That time I read it last. In the hydraulic press, there's a force here. You have to apply a force here. Force here for. Then the pressure. Then there's a liquid inside this stuff. There's a liquid in it. So if you apply a force here, there will also be a force being released out here. A hydraulic press majorly is a simple machine. There's just like if you can go back to your O-level format, you remember that for simple machine, you have to apply a particular a small load to have a massive, a small load, which is called the effort, to experience a massive load, the force out. So now, but what the major principle behind it is the Pascal law. The Pascal law says that whenever this process is occurring, the pressure is always constant. In any liquid, the pressure inside that liquid is always constant. If depending on how the state of the liquid is, inside any liquid, the content of that liquid, provided that liquid is uniform, the pressure inside that liquid is constant. So take note, at any point inside the liquid, at any point or region in the liquid, the pressure is constant. I said the pressure at any point in the liquid is always equal, and the pressure also increases with depth. So there are also some questions that I dropped under this part that has to do with density. The study of, I said hydrostatics is the study of fluids. So I have some questions that we'll be looking at in this case. In a laboratory, seawater with a density of seawater is 1.02 times 10 raised to power 3 kilogram per meter cube. Was mixed with human blood. Seawater was mixed with human blood. The density of human blood is 1.060 times 10 raised to power 3. So now, the mass of seawater is, we're told that the mass of this one was 16 grams. And the mass of the human blood is 8 grams. So now, if you want to solve this question, we're told to find the density of the mixture. Like I said earlier, you cannot find the density of the mixture by just simply adding these two values together. It won't give you the density of the mixture. It's just like you say, this is a biro and this is or rather, let's call two fluid. this is Fanta, this is Coke. Both of them have a bottle of Fanta and a bottle of Coke. Then both of them have their various density. That density is constant anywhere you take it to. But whenever they mix together, their density is going to, the density of the mixture of it is going to be very different. It's going to be very much different, because in the sense that you cannot add both of them together to get the density of that mixture. There must be a reaction that must occur between them. The only way you can get the density is by getting the equivalent value of the density of the mass of each of the various substances. Adding the mass together and the volume together will give you and solving for the density will give you the density of the mixture. Because density on its own, its value varies when a mixture, or the value of the density of a mixture is different from the value of the density of each of a component added together. So this is what I'm trying to say. Now, we're already given the density of this one. You have to look for the mass of it. So density normal is equal to mass over volume. So now the mass, rather the volume, you look for the volume of it. The volume is mass over density. So it will be 1.02 times 10 raised to power 3 divided by the density of this one. Okay, the mass is 16. Sorry. 16 divided by 1.02 times 10 raised to power 3. Then for the other one, this is mass of volume of salty water. Then the volume of the human blood is this. The value is mass over density. So it's 8 divided by 1.060 times 10 raised to power 3. So let me use my calculator and see what my value will give me. 16 divided by bracket 1.020 times 10 raised to power 3. Okay, if you divide that, this is what it will give you. It will give you 0.0157 meter cube. The volume is a meter cube. Same thing with this. The volume of this is 8 divided by bracket 1.060 times 10 raised to power 3. If you do that, you'll be having 0.00755 meter cube. So you'll be having 0.077755 meter cube as your answer for this one. So now, after having this value, now you now have to add you simply add the value of the two masses and the value of the two volume together. So if I add my volume for the first one, 16 plus 8, the mass of mixture, to be giving you 24, I think so. 16 plus 8, 6 plus 8 is 6 plus 6 is 12. 12 plus 2 is 14. 4 remainder one. Okay, 24 grams. But take note, we need our value in kilograms. So we have to convert this to kilogram. Divide by 1000. 24 divided by 1000 will be giving you 0.0123. Which will be giving you 0.024 kg. So now the density of the mixture will now be equal to the mass of the mixture divided by the volume of the mixture. What is my mass of mixture? I have 0.024 divided by the volume of the mixture, 0.0075. So if you are using this to solve, okay, I didn't add the volume of the mixture first. You have to add the volume of the mixture. If you are to add in the volume of the mixture, will be giving you, add this value and this value together. I didn't add it, sorry. 0.0157 plus this value, 0.0075. You'll be having 0.0232 as your value in meter cube. So now, this is the volume of value I'll be picking here. So it will be 0.0232. So if we divide this, let me see what it will give me. 0.024 divided by 0.0 232. At the end, you'll be having this as your value. Having this as your value 1.0345. Take note, density is measured in kilogram per meter cube. So just try and grab every stuff we did here, all the formulas, take them with you. Then some of the theories I made while some of the theoretical aspects I made while solving, make sure you adhere to it. Then take note, if you do all this successfully, you have already gotten an A in your exams. If you have any question, you can also comment, place